We continue with concrete gravity walls, which is the first type of retaining walls we're going to look at. And I would say they're the simplest in some ways. They are. They're definitely a very common form. You see many of them in different types of applications and different types of structures. So the opening slide here shows you some of the terminology that we have. Actually, they talk about retaining wall terminology in general. And but it's largely centered for concrete gravity walls. So, but it's good reference to have, because you'll hear a lot of these terms used again and again and again. Basically, the object of retaining walls, of gravity retaining walls, is that they use the weight of the wall or the weight of the wall in conjunction with the weight of the soil that they trap to achieve stability. And we talked about the last time there were several types of stability, and it probably would be a good idea to go back a couple of slides and talk about external stability, because that's what we're going to focus on with these walls. You've got sliding stability, which basically is the wall's ability to resistance horizontal movement. Overturning, basically is a moment type of resistance being tumped over. Bearing capacity for this type of wall is important because they normally have a flat surface on the bottom of them, and those are subject to bearing capacity failure. And last but not least, deep-seated stability. So we go back, and there are several ways that these are addressed. One of them is through the classic gravity wall, which is kind of at the top here. It's a kind of a triangular structure, and basically it has a weight. It has a center, and that weight is concentrated in a resultant through its center of gravity, and it has earth pressure forces basically attempting either to slide it or overturn it over here. And these are described using, it has a normal component, it has a tangential component, because it is due to the gravity acting on the soil, which in turn acts on the wall. Resisting that, in addition to the weight, is the bearing capacity at the bottom. And also, actually it's two ways. And we talked about this with bearing capacity, and I said at the time that bearing capacity, we talked about incline loads and whatnot, and I told you that the way we deal with these with retaining walls, and probably the best way to deal with them, period, is to break them up into horizontal and vertical components. The horizontal component, the vertical component, we'll start with that one, is straight down. It does not have to act through the center of the bearings, of the bearing surface in the bottom. In other words, it can be eccentric from the center. Just because, it's, and just because you've got this force, you have these forces, and they're going to all act on this, and the resistance to that comes in the vertical direction, and it doesn't have to run through the center. And that's an important consideration. There's also a horizontal force, and what resisted is basically without any other assistance. We'll talk about keyways eventually. We'll talk about piled walls. We'll talk about other things. Without any other assistance, the only thing that keeps this thing from sliding is Coulomb friction. So therefore, what we're going to do with these walls, we're going to analyze on the bearing capacity side, the vertical force using classic bearing capacity analysis, and the horizontal force using sliding Coulomb friction. In a nutshell, that's the way they're analyzed. A cantilever wall, which is what we're really going to focus on, is a wall where instead of having lots of concrete like we have with here, we reduce the amount of concrete. And basically what we're going to do is we trap a segment of soil. And normally what we do is we consider all the soil from the heel back to the wall as trapped. It's all trapped in there, and it helps in keeping the wall from overturning, and to an indirect sense to keep it from sliding as well. In other words, that particular piece of soil becomes part of the wall itself, and we're kind of leveraging that the weight of the soil in that endeavor. So that by doing that, we reduce the amount of concrete available. There are some downsides to doing that. The biggest downside is that we significantly reduce the moment of inertia of the concrete to bending and internal stability problems such as breaking down here. Because as the name implies, this is a cantilever wall, and this acts as a cantilever beam. We're not going to get into that particular part of it, but it's pretty standard concrete design. We don't normally like to do fancy stuff for most geotech applications. So and the last one is a counterfort wall. The only difference between a counterfort wall and a cantilever wall is a counterfort wall attempts to address the problem I just mentioned, and it does so by, instead of having just this and then come to the end and go that way, it has some ribs it puts in there, as you see in this little section A-A. And all this is, by the way, is in your book or in your slides. You can look at either one of them. I'd recommend the book personally. We're going to pretty much follow the book in this presentation. Importantly enough, and this is another thing why this is nice, all of the your definitions, your location of the resultants, your criteria for eccentricity, which is important for down here, your factor of safety against sliding, the applied stress at the base. They don't, for some reason, they don't get an overturning. I'm going to get an overturning. I think overturning is important. You'll see it again when we get to obviously MSC walls and also sheet piling walls. So all those things will be taken into consideration, and global stability. Now, that's one thing we mention in this course, but we don't really analyze it. Global stability with a wall is a little complicated, and as a result, what we see today is things such as this. Now, if this looks suspiciously like your slope stability, well, it should, because what we do here is exactly what we do with, and this is a good illustration, we do exactly what we do with slope stability. We model the wall, we look for a weak failure surface, a circular failure surface generally along, but the circular failure surface in this case not only has to meet other criteria, but it also must be outside the wall. If this goes through the wall basically stops the failure surface. It has to be outside the failure surface. You will note up here is this nice funky looking chart. What that is that this soft piece of software, just like the software you had in soil mechanics, analyzes all of the slope, they can find all of these slope circles and determines the slope circle with the lowest factor of safety. But it also, in this case, records all the other ones. So therefore, you have this nice colorized chart where this yellow area is a low factor of safety. And by the way, if it gets below 1, it goes orange and eventually red, where you can see the factors of safety over here. Typical FEA approach. It has the lowest factor of safety, which mercifully is 1.544 in this case. It also includes the loads on top of the wall, because the wall is additionally, in this case, being used for an abutment. So you've got vertical loads from up here. We're going to avoid that particular issue at this point. It also has loads for surcharge loads along the wall. It also shows you where the failure surface is for the wall itself. It shows you how they've put a little thing in here to break that failure surface. And so we also analyze for global stability. This is probably the best way we have for analyzing for global stability. But you must understand, notice that you have this so-called the low point, and it searches all of these. All of these points, all these colors and whatnot, represents points where the center of the circle has been analyzed and the factor of safety has been computed for that circle. And it keeps looking for it. Usually, like if you remember with your slope stability, so it uses a grid optimization. We had this nice little grid with the lines here and the lines here. And it would check every one of those points to find out where the lowest factor of safety was, where the circle most likely to have failure was. Well, that's true also with this one. This one does exactly the same thing. It's more sophisticated. And of course, the price per seat for software like this isn't anything to sneeze at either. So but it gives you a fairly accurate view of where global stability is important. It is not something that we normally deal with in an elementary solid mechanics and foundations course, but it is important, and you need to be aware of what it is and at least how it's analyzed. And I think when you see this and you connect this with what we did with slope stability and solid mechanics, and by the way, on my side, I'll try to furnish a link to the slope stability in case you've forgotten how that slope stability software actually worked. So that's what you need to do. Is to connect those two and realize this is something we did before that we're going to do. We're going to reference again. Okay, continue. Typical dimensions. You know, a wall designer says, where do I start? What are typical dimensions? Don't say just because it's a typical dimension means it's going to work. What it is, it's a starting point. If you can end it there, I mean, good for you. If it's economical and meets all the other criteria, then typical is fine. But these are good typical dimensions. It also shows you this counterfort wall. You'll see in a little bit easier format using this nice isometric drawing, the ribs, which give greater structural integrity to counterfort wall. The geotech analysis of a counterfort versus a cantilever wall are identical. It may be a little bit more weight due to the fact that it's concrete rather than soil, and we can probably neglect that. But for the counterfort is strictly for structural purposes. And here's a nice step-by-step designing place for cast-in-place walls. These walls are cast in place. They're cast in place with their reinforcement. They're like any other, there's going to be some tension it needs to be reinforced. There's also usually a mat at the bottom for the bearing capacity, and those the vertical and the horizontal reinforcement are generally tied together. Let's go to the design example. This is in your book. You can follow along in your book. We have a nice wall here, and it's a little. I'll show you. Note carefully, this wall's got a lot of the little traps that you see in the geometry of these things. First trap, you've got this wall here is 8.5 feet from this surface here to the heel, and then it's 2.3 across the bottom of the base and another 2.3 to the toe. The toe is important. That's where we're going to check for overturning. We assume that a cantilever wall will overturn around the toe. We have this depth right here, 5 feet is from here to here. That's important because normally in bearing capacity analysis, you've got one of the tricky things. And remember in bearing capacity, you had this nice soil, and then we had this thing under it, the base of the foundation, and the distance from there and there is d sub f. Now we have this mess here where you've got two different depths. Well, it's easy to solve that problem. The d sub f is right here on this side of the wall, not over here. We don't worry about this. We worry about this. Then, if that wasn't enough to make life miserable, we've got this 10-degree backfill slope. And that gives a little extra complication to the problem. We have noticed also that the soil properties are different here, where their phi is equal to 30 and the the unit weight is 115 PCF, and the soil below here is different. It has a phi of 38 and a gamma of 120, which is obviously going to be important for your bearing capacity analysis. So you have to watch stuff like that. One of the things about retaining walls, and we'll see this again with a vengeance in MSE walls, is that the properties of the soil in different parts of the wall don't have to be the same. In fact, in real walls, you can also have layered soils on this side, and that's where things really get exciting. But we're going to try to avoid exciting things like that. The first thing, and this is step by determining the height of the soil exerting pressure. With a cantilever, as long as there's level backfill, the distance from here to the top of the wall is that distance. However, we have a unlevel backfill with a sloping backfill, and you have to add a little distance. In other words, the distance you add is the distance from this surface to where this forms a little triangle here. This is 10 degrees. This angle is obviously 80 degrees, and that's a right angle. And so we have to add the distance from here, where it's the top of the wall, to where it's at the top of the soil at that point. And this is at the point directly straight up from the heel to the surface of the soil. You have to add this is the total distance of the soil acting. That's the distance of the X. That's the really big downside to using a cantilever wall, the soil behind a cantilever wall. In addition to the fact it doesn't weigh as much as concrete, although the difference is not is important, but it's not, it's not order of magnitude or anything like that. 120, 110, suppose 150. The other thing is that the soil, if you've got a upsloping backfill, you've got a longer distance here. You'll notice that you have two components over here, horizontal component, vertical. We're going to get that at 10 degrees, 10 degrees. Second, so we do that. We add that little thing as 21.8 feet. If you were to lay this out in CAD, you could get these quantities directly. I strongly suggest you lay it out in CAD, and you're going to see why in just a minute. Strongly suggest that you lay this out in CAD. Second, compute the coefficient of active earth pressure by using the equation of Ka in this figure for a vertical base, which is, in other words, this is vertical, so therefore theta is equal to 0. You remember in our review in your Soils and Foundations reference manual, the Ka is, or all the Ks, or Kp for has the angle of the back. We're assuming this is a vertical surface, and therefore theta is equal to 0. Again, if you had the one with alpha base, it would be alpha is equal to 90. So, and all you do, we know what the angle of the wall friction is 10 degrees, so that's the beta angle. That's the delta angle there. The beta is the angle of the fill slope. It's also 10 degrees. It happens to be the same in this case. And the internal friction angle soil is 30 degrees. We plug, we chug, we get a Ka of 0.35. We get that's Coulomb theory. If it were Rankine, it would be different from that, or log spiral. But they're assuming the Ashto pair of Coulomb for active and log spiral for passive, although we're not going to actually deal with log spiral earth pressure coefficients in this case, because we're not going to deal with passive earth pressure coefficients. We're going to ignore any passive resistance of this. Now, the wall is going to be going in this direction, and in theory, we will have passive. We normally ignore those. They're too dependent upon the quality of the soil on this side. And if they're just leveling it up, the compaction may not be too hot. And if we try to rely on that, we'd be in big trouble. So we're not going to rely on that for this. Now we go to the next step. compute the magnitude of the resultant active pressure per foot of wall into the plane of the paper. In other words, we want to know the active pressure per foot of wall, the resultant. And when they say the resultant, that's a little confusing. The resultant is a force. And basically what we would, if we've got a uniform soil here and we've got a uniform unit weight, the pressure increases uniformly. And as a result, the pressure is 0 at the surface and then increases to some value down here. We take the resultant of that. We want to know the PA, this quantity right there. We simply 1/2 Ka gamma h squared. This is straight up application of our lateral earth pressures. But what we're trying to do is to get the resultant as this is a little confusing because the resultant is a force. That force in turn is due to earth pressure, which again increases linearly here. So we have this, we substitute this all, we get 9,564.2 pounds per foot of wall. Or if you like kips better, it's 9.56 kips per foot of wall. I think kips would probably be better, but that's not the way they did it. Either way is fine. The only thing you would have to do is instead of having 115 PCF, you would have 0.115 KCF, which you see that in some military documents. You don't see it very often anywhere else. So we'll continue on. All right. Step 4, resolve PA into horizontal and vertical components, and therefore it is the sign of beta, beta being the backfill angle. So therefore it has cosine beta and sine of beta. So therefore we resolve those into 2 because this force, because of the backfill, acts at an angle. Therefore the horizontal force, the force this way, is the cosine of beta. So you just multiply that by cosine of 10, you get 94/18. The vertical, there's also a vertical this way on this, and that becomes important, is PA sine B, 9564.2 times the sine of 10 is 1660. Now, okay, we've got that. And by the way, we're looking at the distance from here all the way up to here. Bottom to the top. In other words, from right here at the heel all the way to the soil surface. That's where the resultant comes from. 21.8, which you computed earlier. So then the moment, now you say, what's this moment arm business? Well, the moment arm business is to analyze. There's 2 reasons for it. One of them is we want to know the location of the vertical resultant on the surface, and we want to analyze for overturning. Okay, so we put the moment arm of pH around point A, basically around, now this is point A. Point A is the toe. That's where we take our moments, where we've decided for purposes of this that that's going to be our origin of our coordinate system, is that point right there. So the moment of the horizontal force is very simply this dimension from here to here divided by 3. It's as I said, it increases a triangle force. So therefore it's this length divided by 3 and that moment, and you get 7. Let's see, it's a little, and the moment arm is 7.27 feet, which is equal to the little b dimension, and then the vertical, actually as a moment arm, you've got this S and the eccentric, it's this right here. The distance from the toe to the heel, you have this, which is 2.3 times 2.3 8.5, this whole thing, which is 13.1 feet, which is the total width of the base of the foundation, which is subject to modification, by the way, in case you suddenly realize that either your bearing capacity or your overturning or your sliding doesn't work anymore. So, with that in mind, you say that's the little g dimension. Okay, So you need to know those two moment arms. This again is where your vector statics doesn't do you a lot of good. In vector statics, we'd have this coordinate here for this point right here, and then we do the vector multiplication and all that. Now, we don't do it that way for this particular case. We have a moment arm here, we have a force here, it has a moment like that. Notice, interesting, that the vertical forces actually go opposite of the horizontal moments created by, the horizontal force moments are in opposite directions. This is going to be helpful. Okay, continuing onward. Determine weights about the toe of the wall. We have these forces that give moments here, but another, which are actually, in this case, counterclockwise, are the weights of the wall. And now you probably would wonder, you're looking at your book or this, and you're thinking, what is this little 1 with a circle, and 2 a circle around it, 3 a circle around it, 4 a circle around it? Well, basically what they are, and of course we've got 5 with a circle around up here. What are they? Yeah. Well, what they are, what we're doing here, there's 2 ways to compute the area, the weight per unit wall of, say, this whole mass. We've got 2 things going against us. One of them is that the geometry is a little funky. We've got angled things here. For example, this base is 2.3 feet at the base wide, but only 1.6 at the top. Why is that? This is a cantilever wall. Cantilever moments you're going to have down here at the base. So that's for structural purposes. So therefore, we don't have a nice rectangle. And the nice rectangle is important because the weight of this plus the weight of this is equal to the area of this wall. The weight of this wall per unit is the weight of this wall times the unit weight of the wall, which is 150 PCF. And the weight of this soil is the weight of this area here times the unit weight of the soil, which in this case is 115. Now, that's important to note because there are 2 approaches we can take in solving problems like this. One of them is we can do the way it was done here. What they've done is they've divided this up into 5 areas. There are 3 rectangles, which are 1, 3, and 4, and 2 triangles, which are 2 and 5. Each of those have an area, and each of those have a centroid. And if they have an area, they have a unit weight for that area. They have a weight per foot of wall. If they have that, and they have a centroid, then they exert a moment around here. And that's what all these calculations are all about. The net moment around this thing right here. And in fact, all of these, actually, all the weights exert a counterclockwise moment around A. In other words, for example, this is an easy one. 3, area 3 is equal to this height times this length, which is times, and that gives us an area. The centroid is obviously in the middle of it, is equal to this distance divided by 2, and therefore, and that's where you have what this is all about. That's one way of doing it. That's the old way of doing it, really, and it's the hand way of doing it. There's another way you can do this as well and save yourself a lot of time and a lot of trouble. And that way is to use your CAD software. If you laid this out in your CAD software, which I suggested earlier, then what you would have is you could compute, instead of, you've got 2 different, first of all, that reduces you to 2 different areas, and because you got 2 different unit weights. You can't combine things that don't have the same unit weight for the purposes of this calculation. What you can do, however, is take the wall, for example. You can trace this out, lay it out, trace it out. You can get the area. The CAD software will give you the area of this, and it will give you the centroid of it. Centroid. So, and that area times the unit weight of concrete would be per unit weight of the wall times the centroid, the distance from here back to here along the x-axis is the weight, which acts downward in case you just as a reminder, is the weight along is the moment. You can do the same thing with the soil. Now, if you've got level backfill, this is just a simple rectangle. The weight is halfway across, but you don't have one, so you can just do this whole thing. It'll give you this area times the 115 PCF. You get your unit. You get your unit. You get your weight per foot of wall times this distance from this centroid of this area back to there. That will save you a lot of trouble. One of the things that I think CAD software people don't understand about CAD software is it can be used for a lot of simple geometric constructions that we used to do by hand. CAD software would considerably simplify this particular piece of analysis right here. Next step, check the factor of safety against sliding. Neglect the passive resistance of embedment, which I told you to do earlier. The factor, this is straight up block on horizontal surface statics. The forces this way are the weight, all these weight, plus the vertical force along this surface. Those are the two vertical forces acting down. Times the tangent of the friction angle here, and this is where you can trip up. There are a number of ways of computing delta B, this friction along here. They use 3/4 of this phi right here. Make sure if you're given something where you use a certain portion, for a friction factor against the soil, that you use the right soil. The soil here, this is where the soil down here and the soil up here are different. So you need to read your problem carefully and make sure you know which soil is which. So you do that. And 28.5, you could also look it up. They also compare it with the NAFAC chart, which we showed you last time. I am normally a little more, in my problems, I'm normally a little more specific in what I want. And that's mostly for my benefit as much as yours. So, but in any event, that's how you figure that out in more of a real life situation. You can use the NAFAC table if you like. That's obviously permitted to you. Okay, but that gives you the depth, and you plug and chug, and you get, and then pH is the horizontal force, which is trying to put. In other words, basically, it's the same old thing we do with retaining walls all the time. It's sliding forces. We have resisting. The resisting force is basically the frictional force along the bottom, and the driving force is this pH right here. And the ratio of those two is your factor of safety. So we do Fs of this. You plug into this equation right here. You get this, and you get a 1.72, which your book triumphantly declares is okay. I'm not sure what factor of safety that they gave you. Now, I've seen some problems students say, well, this is a great factor of safety. Well, if you say, sometimes I don't ask for that. It's usually I say, compute the factor of safety. If I ask you next, is this design acceptable? Then you need to make a declaration like this. If I don't, I wouldn't do it. Some students like to do it that way. I would not run the risk of doing problems like that. So I would just answer the question. Okay, unless I've given you some kind of... Now I added this, and this is not in your book, the factor of safety for overturning. Basically what I've done is really kind of simple. And I want to, the factor of safety for overturning is I compute this moment here is basically your resisting moments over your driving. The driving moment, the resisting moment is the one, this I actually computed back a couple of slides ago, is this thing right here, based on the weight. Plus, I've got a little additional help, not a lot, from this PV times this moment arm here. The driving is basically the horizontal times this moment arm here. And I computed all of these earlier. And I get a factor of safety from overturn 3.4. You know, we're going to get into the middle third issue, and there are some books that will tell you, well, you know, if you can keep the result in the middle third, you won't have overturning. I personally kind of prefer the belt and suspenders approach. You know, check for overturning. You're going to have to do that with other retaining walls. You have to do it with sheet piling for sure, and for MSC walls, you have to check explicitly for overturning. So I think for consistency's sake, check for overturning this way. And I added this. Your book doesn't have this, and I did add it. Okay, next, check the limiting eccentricity and factor of safety against bearing failure. Compute the, you know, and all that involves is this. I compute the limiting I'm trying to compute whether this thing is in the middle third. That's fairly simple. Basically, it is equal to the resisting moments minus the overturning moments. You take the moments here, which I computed those, and the overturning moments, which I've also computed, which I'll just plug and chug in. You can trace these back through your problem to where they came from. But the resisting moments minus overturning moments is the net moment at this point right here, this point A. And then the shear are the four. In other words, these moments minus the resultant force on this, the vertical forces, which is why they have summation of V, are, you know, you divide the two and you will get a moment arm. That's what you're aiming for here. In order to compute, and you remember this from the middle third thing we did with the bearing capacity analysis, what we want to know is whether the resultant force is within on the base of the foundation. The resultant vertical force is within the middle third. That's what we want to know. That's an additional check. And so therefore, I simply substitute these moments over the resultant force on this thing, and I get a moment arm of 5.55 feet, which from here to about somewhere in this area, it's about 5.55 feet. You know, 2.3 times plus 2.3 is 4.6 feet, so it's somewhere over around here. That's the resultant force, the location of the resultant force on the base of the foundation. And then I check to see if it's in the middle third. And I use the same formula that I used before. I compute the eccentricity. The eccentricity is equal to B over 2 minus D. B over 2 obviously is the centroid of the foundation, minus the actual location of it is the distance between the two. As long as that is below B over 6, we're in business. And that's exactly the computation that it shows. It says basically the distance from the centroid to the actual resultant is 1 foot. And 1 foot is lower than, and B over 6 is 2.18. So therefore, it's okay. It's okay. Then we have number 3, compute the maximum and minimum pressures. This is straight up from what we did before. Now, it should be obvious. One thing you could do if you really wanted to would be to go and compute the maximum pressures, minimum pressures. No, and skip this. These two calculations, in one sense, are redundant. In another sense, they're not, because some this particular I'm not exactly sure what they're doing here. Is basically saying that Q alt is 20,000 PSF. It's sort of a presumptive bearing capacity approach is what they're doing. That's what they're just presumptive bearing capacity approach. I'm not sure why they're doing it that way. The formal way to do it would be to do the following. Once you've established this in the middle third, the formal way to do it would be to actually compute the do a reduced foundation, is the B minus 2E type of thing, and then do a bearing capacity analysis. That's using this soil as your soil. That's the formal way of doing it. That would be the nice way to do it. Cantilever example. There's a few things. I talked about global stability earlier that would definitely apply in this case. You can see this is very similar to what you had before. The summary basically is everybody's giving each other the high five with this summary. And I guess that's okay. I don't like their bearing capacity analysis. I really don't. So I think you'd be better off. Another thing they didn't even touch is the issue of settlement. You could run a settlement now. You could take the same reduced foundation, B minus 2E, reduced foundation, and you could run a settlement analysis using Schmertmann's or Huff's method. Settlement is important with retaining walls. It should not be ignored, particularly with very soft soils. Many retaining walls like this are founded on good soils. If they're not, they very frequently will put piling or some other type of deep foundation under it. But if they don't need deep foundation, they need to be checked for settlement. Or if they're kind of in a middle sort of thing, they need to be checked for settlement. Settlement's important. Okay. These are common factors of safety that you have, and I think that's where your book probably is why it declares victories, because it meets those. It would have been a little nicer for everybody if everybody declared those up front. But make sure. But again, the important thing is, if you're going to evaluate, there's a difference between evaluating, in this course at least, between evaluating a factor of safety and deciding whether that factor of safety is acceptable. Many times computing a factor of safety is one thing. Deciding whether it's acceptable enough, that's a different story. Lateral squeeze. Particularly in situations where you have additional loading, you will get lateral squeeze. And basically what that means is this: you've got a load here, you're pushing down here, and by retaining, if you remember from lateral pressure theory, you push this way, you get this way. That puts additional loads on the wall. That, with otherwise reinforced walls, otherwise without stuff like this could lead to a very unacceptable settlement. And in some cases, with very soft soils, this doesn't always work the way it should. But in some cases, you can actually you would actually add, and we'll see this with sheet piling. for sure, and maybe even with MSC walls, we will see like a uniform surcharge added, which will actually up lateral pressure, where we can take lateral squeeze into account. But with very soft soils, very frequently you get lateral squeeze, because in soft soils you get fairly substantial volume. One of the things that theory of elasticity and in mechanical materials in general deals with is the fact that if you have a soil, if you have an element of material, that material element, you not only have to take into consideration the stresses this way and this way, but also the fact that the volume, you have to maintain the volume of the material. The material will compress to some degree due to elasticity, but it will also, in some cases, but if it does, very frequently, the volume requirements, essentially you have to keep a continuity of volume. In other words, a preservation of volume, conservation of volume. In other words, it'll decrease a little bit, but it may not be anywhere near enough, particularly with soft materials. So you have to keep that in consideration when you're looking at the way materials respond to loads. But in any event, we have some factor of safety against lateral squeeze here. Key foundation for sliding resistance. There are a number of ways of dealing with sliding resistance. One way that is very common is to use a key, and basically what it is a little ridge of concrete that sticks down and basically creates passive pressures against it, and that adds some additional resistance in the horizontal direction. That can be very useful in some cases, especially if the soil under the retaining wall is fairly competent. If it's not going to do a lot of good. If it's not that competent, you're going to have to essentially use a deep foundation. But if it's fairly competent, but it needs help, this is a very inexpensive option. Obviously, the one thing you'd have to make sure of is that if you actually excavated the key before you pour the concrete, that the excavation will hold up. In other words, that you won't have it so either the soil is so soft or cohesionless that it would just collapse if you tried to excavate it. Or you could build a form as well if you've got that kind of problem. But if it's not, you can usually dig into the soil, excavate the nice ditch in the soil, put the reinforcement in, pour the key. The key is a fairly economical way of dealing with the need for additional horizontal resistance to movement. Failure causes for retaining walls. I probably should have put this sooner, but for some reason this has always been at this point in the course, and so this applies to all of them. What makes retaining walls fail? Okay. We've looked at, I think maybe this is a good because we've looked at the nice engineering calculations behind this. We've looked at the possibility of designing against overturning, against sliding, against global failure, those kinds of material failure. But the problem is that very often retaining walls, even if they are designed under the best of criteria, and a lot of times they're not, unfortunately, particularly walls like this. You still get failure. What's the problem? The number one cause of failure in retaining walls is missing or inadequate drainage systems. And that's particularly true with walls with cohesive backfills. I told you earlier that cohesive backfills are not a good idea because of the issue of you have with a cohesive backfill, you have water build up on the back on the wall, and you get unbalanced hydrostatic forces. That's number one. And the the right after is the unsatisfactory definition of wall base. But for the need for drainage behind walls cannot be understated. You can design the nicest wall in the world, but if your water table builds up hydrostatic pressure behind the wall, you're going to have problems. And the other one is, and the reason why is the second part of it, which is at the bottom, is the backfill is clay. Clay backfills are frequently unavoidable with retaining walls, but they're never necessarily desirable with retaining walls. So how do you deal with them? I don't spend a great deal of time, but retaining wall drainage is an important issue, and this doesn't just apply to cantilever walls. We're going to see this again with sheet piling. Sheet piling has the same problems. Virtually, some types of walls are traditionally leaky. In MSC walls cases, we're going to see you don't have the cohesive backfill issue with an MSC wall, so you don't have to worry about it. But with retaining walls, with most retaining walls, especially the way you deal with it is you create a drainage system behind the wall that draws the water away from here, eliminates or reduces the unbalanced hydrostatic forces, and pushes the water out through the bottom. Very often, if you can't have water coming out this way, you will drain it this way through a longitudinal pipe, and what calls a drainage blanket. A drainage blanket is simply how do I want to put it? An area, usually it's fairly flat, or it's much wider this way than this way, of free draining soil, traditionally gravel. You would have a filter with it. We talked about filters in Dirt 610, which can be either soil, geotextile, or both. That basically allows water, shortens the drainage path from a impervious, relatively impervious cohesive soil into a very pervious cohesionless soil. And these are good strategies to use. A good drainage system should never be neglected with any retaining wall system. One way or the other, the water has to be gotten rid of. And it needs to be gotten rid of in a reasonable fashion, because what you're basically doing with any retaining wall is that you are creating a discontinuity in the elevation with the retaining wall. And the problem with water is that frequently, if water has been there at a certain level, say over here, before you create the discontinuity, chances are at some point it will be there again afterwards, after you've left. So you need to make provisions to drain that water away and to lower its level so that it doesn't become a source of problems for your retaining wall. Okay, that concludes cantilever walls. Thanks for watching, and God bless.